So 3.2 is solving systems algebraically. So our goal today is to solve systems of linear equations using substitution and elimination. So we're going to do substitution first, and then we'll do elimination after that. Substitution. The very first thing you're going to do is you're going to pick one of the equations, and you have to get a variable alone. Okay, so you're going to get a variable alone. Doesn't matter if you use equation 1 or equation 2, or in this case, they're labeled A and B. But you're going to pick an equation or a variable and you're going to get it alone. Once you have that variable alone, then you are going to substitute that expression into the other equation. Once you do that, you'll notice that you're going to have an equation with only one variable. Just like we did in those last two example problems, so you're going to have an equation in one variable, so you'll solve for the variable. Then you'll have one of your variables because your solution is a point. You'll have either x or you'll have y. Then you put it into that point. Right? Your solution is a point, so you'll put it in the correct spot. Is it an x or is it a y? Once you have that variable, then you get to choose whichever equation you want to use. It doesn't matter because that is going to be a solution to both of your equations. It doesn't matter which one you pick. You're going to plug in the known variable and solve for the unknown. Okay, so you'll solve for that unknown one, and then you write your solution. Because now you'll have x, you'll have y. You write your solution as a coordinate point. Because just like when we were graphing, that's what the solution was. It was where the two lines intersected, which was a point. The last step is to check your solution. It's always important that you check your solution because you will know before turning in your quiz whether you have it correct or wrong. And if you don't have it right, I would suggest going back and trying to find your error if you can see that it is not the correct answer. Okay? So it says solve each system by substitution, check your answers. State whether the system is independent, dependent, or inconsistent. So the very first step it says is to get a variable alone. Do you want to solve for x in A, y in A, x in B, or y in B? Which variable do you want to get alone? The first x, the second x, the first y, or the second y? The first y is going to be the easiest one to get alone because it's already doesn't have that coefficient in front of it. So we're not going to have to divide. If we had to get this 3x alone, we'd have to subtract the y and then divide everything by 3, and we'll probably end up with fractions, which is not the end of the world. But if we have to divide everything by 3, or divide everything by 2, or divide everything by -5, then there's a better chance that we're going to be dealing with fractions, and a lot of times people don't like to deal with that. So if you pick the one that doesn't have a coefficient, well, the coefficient isn't written in because it's 1, the y here, that's a little bit easier. to work with. When you solve, you'll get y equals negative 3x plus 3. Are we okay with how I came up with that? Okay, that is another version of A. Those are the same equation, they're just written differently. Okay, so that goes back to when we were doing stuff in 2.2 with writing linear equations. It's the exact same function, it's just that the equation can be represented in multiple ways. So, then it says get a variable alone. Did that. Substitute that expression into the other equation. Since this is representing y, this is y, what I'm going to do is I'm going to plug it into y down here. Because y equals this expression, I'm going to replace y. I'm going to substitute y in as negative 3x plus 3. So I'm going to write this out. 2x minus 5. My y is what I'm going to substitute in. Negative 3x plus 3. That's what I fill in there. Is that okay? Is this ringing a bell? Yeah. Okay, cool. Now, notice that this equation is only in one variable. I only see one variable. What's the only variable I see? X. I can solve and get x alone because we just practiced that, and you guys were like, oh, that's easy stuff. We've done that before. So get x alone. First, distribute that negative 5 through. 2x plus 15x minus 15 equals negative 15. Then what? Combine like terms. 17x minus 15 equals negative 15. Then what? Add 15. Add 15. Goes, oh no, it went away. What does that mean? 17x equals what? I can't do it? Undefined? Oh, 0. Yeah, you can do that. For whatever reason, people always mess this up, and that's why I actually do this as an example. Yes, negative 15 plus 15, there is an answer to it. It's 0. Okay? And then what do I do? Divide by 17. And they're like, oh, no, not possible. Yes, it is. 0 can't be in the denominator, but you surely can do 0 divided by 17. If you don't know, plug it in your calculator. Your calculator will tell you that answer is 0. I have 0 pizzas. I'll share them with all 17 of you, and everyone gets 0, and we all are happy. Right? I had pizza for lunch. All right, so x is 0. All right, we're halfway there then. Now we have a known variable. Now we can plug it into, it doesn't matter which equation you plug it into. You can plug it into A, you can plug it into B, you can plug it into your other version of A. But what variable do we still need? Y. Okay, so we're going to plug in x as 0, and we'll figure out what y is. I like to plug it into the one I manipulated because y is already alone. And if I plug it in there, y equals negative 3 times 0 plus 3, y equals 0 plus 3. Y is already alone, and I don't have to do anything other than simplify that right side. You see that? So, am I done? I found x. I found y. I'm done, right? I'm supposed to write my answer as a coordinate point. So when I see my solution is a coordinate point. X was 0, y was 3, so 0, comma 3. I also have to say the type. If I have a solution, is that independent, dependent, or inconsistent? Independent. Very good. Give me like a 1 through 5. I understand substitution. I think I can handle that on my own. Down to a never seen substitution in my life. I was never taught this before. Mrs. Fox, you're lying to me. This is not review. I don't lie. I'm actually a terrible liar. I can't even lie. Don't ask me to lie.
I can. I always end up telling the truth by the end because I don't
You feel uncomfortable,
I
yeah.
feel so, it stresses me.
I just can't even
like,
do
I'm
it.
a good liar, don't get me wrong,
no.
but once, like, after a week, I'm like, listen, here's the truth.
Yes. On the type. Well, back in 3.1, you have your notes from 3.1?
Yeah, probably.
Okay, we'll scroll back to it. Go 2 pages before. You'll see looks like this. Okay, our type. We have 3 different types. We have inconsistent, independent, and dependent. Did we find a solution here?
Yeah.
Okay, so it can't be 0 solutions, so it's not inconsistent. Did we have infinitely many solutions? No, we had 1 solution, so it has to be independent. Does that make sense?
Yeah.
So you have to resort back to those for the types. Okay, so now looking back at this, okay, there are a couple other situations that sometimes come up. Sometimes when you go to substitute it in, when you go to solve for x, x disappears, and you get an answer that is true, such as 0 equals 0, or 4 equals 4, or -7 equals -7. And if we get something that looks like that, it's a true statement. Agree? Okay, so then what kind of answer do we have if you get a true statement?
Inconsistent?
Yeah. We're going to talk about that in a second. But, okay, so here's your graph. If it's true, it must mean that there has to be a solution, right? And when we were doing like inequalities, remember we had a true statement. Do you guys remember what our solution was with the inequalities versus a false statement? No, what was Avery saying? Not with extraneous. Extraneous was absolute value stuff. Because when you plug it back in, it doesn't always work. But if we had like 4 is greater than 0 and you said yes, what would your number line look like? It was all shaded in. Remember that? Because you had all real numbers. In this case, we don't have all real numbers, but you do have an infinitely many solutions. So what you're going to say is just infinitely many solutions. It's not all real numbers because your solutions here are points, okay? And so what does your graph look like if you have infinitely many solutions? It's just one line because those 2 lines overlap. Remember, that's like if you had this was your line and the second line was right on top. So your solution, it can't be any point. It's any point that's on that line, okay? It's not all real numbers because we're not talking about numbers. We're talking about coordinate points that are our solutions here. And it can't be all coordinate points because not the entire graph is the solution, but instead any point on the line is a solution. That's where the 2 lines intersect, is any point on that line.
Is it only if you have like the lines that are the same? Like
The same line, yep.
Like, only if it's the same line.
Only if it's the same line. And you'll see that when you're going to do substitution because you'll end up with a true statement. The variable disappears. You can't find x if it disappears, and you'll get a true statement. Okay? So when there are no variables and the remaining statement is true, it looks like this, meaning it has to be the same line. What type is that? That's a dependent system. Okay? So if it's false, then this example might look like 4 equals 0, or 7 equals 4, or 2 equals -2. All of those are false statements. Okay? So what would our solution be here? It's not many solutions. It's no solution. Because if it was 1, we would have found what x was. But x disappeared or y disappeared. And so we can't even find any variables. And this time, it's not because there's many. There are no solutions. What does your graph look like when you have no solution? That's when you have the parallel lines. So that's if you have two lines that are parallel. I'll draw those parallel. Okay, and the type is then what? Inconsistent. Very good. All right, next we're going to try an elimination problem. Am I good to flip this? All right. So step 1 is you're going to have to manipulate your equations. You are going to have to line up the variables. You're going to have to line up your equal sign and the constant, which is just the number. Okay, so your variables are x and y. Your constant is the number without the variable. And then obviously the equal sign, you guys know what that looks like. We'll fill that in too. Okay, so you're going to line everything up in your equations. You might have to move things from one side to the other because notice in this example, 3y is on the right and x is on the left. And in example B, x and y are both on the left. You can choose which way you want to do it. Okay, for A, you could either leave A the way it is and make B look like A, or you can make A look like B. It doesn't matter as long as we get both of them so that the X is in the same spot, the Y's are in the same spot, the equal signs are in the same spot, and then that constant's in the same spot. Okay, and what a lot of people tend to do is they always go to standard form because one, standard form doesn't deal with fractions, and also it's always in the same order. X, Y, equal sign number. X, Y, equal sign number. So if they move things to standard form, then you know everything lines up. Okay? Or you can put everything in slope-intercept form. Only problem there is sometimes you deal with a fraction. So that's step 1. The next step is to multiply either one or both of the equations. And you do this so that you manipulate it to have opposite coefficients on one variable. Okay, so if your x has a 4 on it, you want to manipulate it so that your other x has a -4 on it. Or 5 and -5 line up. Or 6 and -6 line up. You want them to be opposites, okay? So they cancel. Yes, that's where the elimination piece comes in. Oops, sorry. So step 3 is to then add the equations together. And when you do this, that's where that elimination process comes in. This will eliminates a variable. So as soon as you do that, one of your variables is going to disappear. Okay? Now you'll only have one variable left, and you're going to solve for the variable that's left. Okay, now you'll have one of your variables, and then you use that in the exact same steps that we did with substitution. You're going to plug that into either of the equations to solve for the unknown variable. So substitute the known variable into an equation. It doesn't matter which equation you plug it into to find the unknown. Variable. The sixth step is to write your solution as a coordinate point. So 5, 6, and 7 are the same as the last 3 steps in substitution. So write the solution as a coordinate point. And the last step will be to check your solution. And when we finish, we'll go back and check both of them, because I know we didn't check example 1 yet. All right, so the first thing we have to do is line up our variables. So do you guys want to make A look like B or make B look like A? You want B to look like A? So you want to move the 4y to the right side? Okay, we could do that. So if you do that, then this one's going to become 2x equals 4y plus 24. And this one is still x equals negative 3y plus 0. I'm going to write that in just so I can visually see everything is lined up. Is that okay? Okay. And that's totally fine if you did it that way. I tend to put things in standard form when I'm doing elimination. I don't know why. It's just what I get in the habit of doing. And so I probably would have said this was x plus 3y equals 0, and then it would have been lined up just like that. It doesn't matter. As long as I can see x's are lined up, equal signs are lined up, y's are lined up, numbers are lined up. Okay? The next thing it says to do is multiply one or both equations to have opposite coefficients. So if it helps you, you can write in this coefficient here as 1. 1 and 2 are not opposites. Negative 3 and 4 are not opposites. So I have to manipulate these so that I do have opposites. Do you guys want to eliminate the x or the y? Which one you guys want to deal with? Okay, let's deal with the x. How can you make 2 and 1 opposites? What one can you multiply, or should you multiply both? Yes, if you take this top equation and multiply by negative 2, that should make that a negative 2x, and we'll have a 2x, and we'll have opposites. So I need to make sure that I multiply everything by negative 2. You can either write it like this, or some people like to write it by showing me that they're going to multiply this by negative 2, and this by negative 2, and this by negative 2. Either way, you always want to leave everything lined up. So this one is now going to become negative 2x equals 6y plus 0. And this one is going to be 2x equals 4y plus 24. Notice, even though I didn't do anything, I still rewrite it so that I can have A lined up with B every time. Okay, that's really important that we do that on this one. Did I do everything okay here? Someone looked at it like I messed. What's that? Negative 2 times 0 is still 0. So still 0. Okay. Now that I have opposite variables, sometimes you might have to do this in a couple steps. Sometimes if you had to eliminate the y here, you would have had to turn negative 3 and 4 into, I think, 12. So opposites of 12. So you could have multiplied the top by 4 and the bottom by 3. That would work. So sometimes you have to manipulate both equations in order to make this work. Okay? So then it says to add the equations together. All right, so now I'm going to add them together. My equal sign is going to stay in the same spot. What is negative 2x plus 2x? 0. 0x, which is just 0. Okay? 6y and 4y is 10y. 24 and 0 is still plus 24. Oh, we're going to get nasty numbers because I was going to change this and I never did. Apparently I changed it on my key. But that's okay. We'll get fractions. We'll learn how to deal with them. Okay. So I have to get 10, I have to get y by itself. So subtract 24 on both sides. Divide by 10 on both sides. That's going to reduce negative 24 over 10, negative 12 fifths. Okay, so when I go to write my solution and my type, my y is negative 12 fifths. Now I'm going to have to do the same steps that I did last time. I'm going to substitute the known variable in and solve for the unknown. So my known variable is y. It doesn't matter which one you plug it into. I would probably, since I'm looking for x, the a is already solving for x. X equals negative 3 times the y value is negative 12 fifths. Negative 3 times negative 12 is positive 36 over 5. That's not going to reduce, so there's my x value. Okay, well, what type of system is this? What is it when I have a solution? Independent. All right, let's go ahead and we'll write what we end up getting with the true or false statements, and then what we'll do is we'll go back and actually check our solutions. I'll show you how to check them. So, if it is a true statement, so you get to a point where there's no variables left and you get a true statement. For example, maybe it says 3 equals 3, okay? What is our solution if this happens, and what is the type? What's the solution if I get a true statement?
Oh, wait, I mean,
It is dependent, that's your type. What is the solution now? And notice this is no different than what we did on the front page. So what's your solution going to be? Infinitely many solutions. Okay, that's the way I have to write it. You cannot write all real numbers because our solutions are not real numbers. They are coordinate points. Okay, so they're an infinite number of coordinate points. And it's not all coordinate points because it's actually any point on the line. So the way we have to write it is infinitely many solutions. Okay? And we already drew what our graph looks like, so we're not going to write that again. If it's false, maybe you had something like 0 equals 4. What is your solution if that's the case? And what is the type if that is the case? No solution. And inconsistent. Okay, so the next thing we're going to do is we're going to go back and we're going to actually check our solutions. So, this is what I'm going to show you. You can check it completely in a calculator. You do not need a to show me the work to checking your solutions. So, our x value here. Let me try to put this where I can see both. I'm not going to be able to see that. Here. Okay, our x value is 36 fifths. Equals negative 3 times the y value was negative 12 fifths. Notice all I am doing is plugging in. I plugged it on the left side and I plugged it on the right side. If they're both 7.2, does 7.2 equal 7.2? Mm-hmm. Yes, it does. So it works for equation A. Now I'm going to do the same thing with B. So I'm going to clear this. 2 times x was 36 fifths minus 4 times the y value is negative 12 fifths. That's the left side. The left side's 24. Does the right side equal 24? Yeah, I don't even have to plug that one in. Does 24 equal 24? Yes, it does. That solution was a solution to both A and B, so I know that that is my solution to the system. Does that make sense? Okay, now we're going to go back and check on the first page too because we skipped that one. So it's good to do. If you want to wait till the end and go back and check them all, you can do that, or you can check as you go. This one, our x is 0, and our y was 3. So 3 times 0 plus y is 3 equals, the left side is 3, the right side is 3. Does 3 equal 3? Yes, it does. So it works for A. Now we have to check for B. 2 times the x is 0 minus 5 times the y was 3 equals, the left side is negative 15 equals, the right side already shows it's negative 15. Negative 15 does equal negative 15, and it also works for equation B. Does this make sense? How we can check our solutions? Okay, it has to be a solution to both equations to be a solution to the system. Okie doke? The rest of the time is yours to work on that assignment. Okie doke? All right.